I am E. Krishna Rao Patro, Associate Professor in the Department of CSC from Aeronautical Engineering College, Hyderabad. So today we will discuss about one important topic, that is AVL tree. I think you have seen the binary search tree in the previous session. So with extension to that binary search tree, today we will discuss about one more tree called AVL tree. The name indicates it's also a tree which will be balancing the tree in terms of height. So AVL tree will be also called as height balance binary search tree. So I can say AVL tree is an extension of binary search tree. So you can read now. AVL tree is a height balance binary search tree. Each node associated with a balance factor, which is calculated by subtracting the height of the right subtree from height of the left subtree. So if you subtract the height from left with height means right, then you will get the balance factor. The tree is said to be balanced if the balance factor of each node either -1 or 0 or 1. Then it is balanced. Otherwise it is unbalanced. So that means what? For every node, the balance factor should be either -1 or 0 or +1. This tree was invented by Mr. Deletion, Welsky and E.M. Landis. So these three persons, they have designed this one in the year 1962 itself. That's why from their initials, they have designed the name called AVL tree. A stands for Deletion, B stands for Welsky and L stands for Landis. Okay. The tree is named after these three mathematicians. They have designed this tree. Fine. It is observed that while storing the data in binary search tree, sometimes the data may go only one side. So when the data goes completely one side, then that becomes one type of linear arrangement. So in the case of linear arrangement, it may take more time for searching. So that is the worst case of searching the tree. So I can say it is a worst performance when the data goes completely in one side. So to avoid that worst performance, they have designed this tree. So that means it should be arranged in such a way that it must be balanced in a proper way, so that it will take less time while searching the data. Because your ultimate goal is to search the data in a very fast way. So to avoid this long time, they have come out with a new idea called balance factor. So this balance factor should be kept in a proper way. AVL trees are also called height balance tree, and the ultimate goal is you have to calculate the balance factor. The balance factor should be either 0 or -1 or +1. And how to calculate balance factor? The balance factor can be calculated by subtracting the height of left subtree with height of right subtree. That means left height minus right height. If you subtract this with this, then you will get a balance factor. Okay. The tree is said to be balanced if the balance factor is between this -1 to +1. Otherwise, it is imbalanced. It is not at all balanced. AVL tree is also one type of binary search tree. Please remember, every AVL tree is a binary search tree. I think already I told you in the previous session, the binary search tree means what? The left child data is always less than parent data and right child data always greater than parent data. The subtrees of every node may be differ by 1 in terms of height. Okay, the subtree of every node may differ in height by at most 1. If the height difference is differ by at most 1, okay. If it is more than 1, then it is not AVL tree. Simply it is a binary search tree, but not AVL tree. So remember, in AVL tree, the height may be differ by at most 1. You can see this example here. 42, then 35. 35 is less than 40, so it comes left side. And 31. 31 is less than 42, but not 31. It's 37. 37 is less than this. Then 19. 19 is less than this. Then 27. Then 14. Then 10. then this is your what? It is binary search tree but not AVL tree, because if you think about this tree, the left side height is more than right side height. So the height is not balanced properly. So it is simply binary search tree. It is only binary search tree but not a AVL tree. Similarly, if you think about this tree also, completely comes towards right side. So it follows the property of binary search tree, but not it following the property of AVL tree. So it is a just binary search tree but not AVL tree. Fine. Similarly, if you want to make the tree to be a AVL tree, then it must be balanced properly. So you have to check always left height as well as right height in every node. So every node should have a balance factor of either 0 or 1 or -1. If these factors are there, then it is a AVL tree. Now think about this tree A, B, C. Now B's root is balance factor is 0 and its left side is A and right side is C. So it is a properly balanced. So it is a AVL tree. Similarly, if you think about this CBA, now if you think about this, completely comes one side. So if you see, the balance factor for C is 2, balance factor for B is 1, balance factor A is 0. So up to B no problem, up to A no problem. When you think about the C, it is imbalance because C's left side height is 2, right side height is 0. So it is imbalance. Similarly, if you think about this tree, A's right is B, B's right is C, it is completely right side, one side. So its right side height is 2, but left side height is 0. So it is imbalance. That's why its balance factor at A is 2. Okay. So it is also not a AVL tree. Now think about this tree. It is a AVL tree. If you see this tree now, it is following the property of binary search tree. At the same time, it is having the balance factor of 0 or 1 or -1. Now for 25, the balance factor is 0 because its left side height is 1, 2, 3, 3 and right side height is 1, 2, 3. So 3 minus 3, 0. So at this node, it is balanced. Similarly, if you think about the 20, for 20, what is the balance? Because left side height is 2 and right side height is 1. So 2 minus 1 is 1. So it is also balanced. Similarly, for 36, 1 and 0. So that means height is 2 and this side is 2. 2 minus 2 is 0. So that means if you think about the entire tree, everywhere the balance factor is either 0 or 1. So it is completely AVL tree. Of course, every AVL tree is a binary search tree also. Now think about this tree. Here also 100 is the root, 100 is left 50, 100 is right 150 and 150 is right 175, 150 is left 125. So it is following the binary search tree property. At the same time, the height also, if you subtract left height with right height, the balance factor everywhere is either 0 or -1 or +1. So it is also a AVL tree. So every AVL tree follows the property of binary search tree. At the same time, it is maintaining the height balance. And what are the operations you can perform on AVL tree? The operations like creation, insertion, deletion and traversal. So all 4 operations you can do in the AVL tree. So while performing the operation, just the operation what you have done in the binary search tree, same way you can do it here also. So there is no deviation, but only the thing is you have to check the balance factor after doing every operation. So in AVL tree, after performing operations like insertion, deletion, we need to check the balance factor of every node in the tree. If balance factor is deviating, then you have to balance it. Okay. So in every node satisfy the balance factor condition, then we conclude that the operation is success. If the operation is not success, again you have to go for balancing. How to do balance? For balancing, there are various algorithms, rotation algorithms. Okay, before that, let us see what are the time complexity for everything. Space requirement is same, whether best case or average case. Space requirement will not change. Searching time is always order of log n time. Whereas in the case of binary search tree, if the data goes completely towards left or right, it is become order of n, because that become a linear. So to avoid that one, you have gone for AVL tree, because AVL tree takes always a constant amount of time for searching the data. Similarly, while inserting also, it takes constant amount of time. That is order of log n. Similarly, deletion also order of log n. So in average case as well as worst case, for every operation in AVL tree, it takes order of log n time. So this is a perfect tree for organizing the data in a binary tree form. So AVL tree also a binary tree, AVL tree is a binary search tree, AVL tree also a height balance tree. The insertion in AVL tree you can perform in the same way as perform in binary search tree. AVL tree is added the node into AVL tree as a leaf node. So you can add one node as a leaf node, but while adding, you have to check whether it is violating the rules of AVL tree or not. If it is violating, then go for balancing. Okay, the tree can be balanced by applying some rotations. So within the rotation, you can balance it. So the rotation is required only if the balance factor of any node is disturbed, because the balance factor should not exceed between the range. I told you the balance factors are like 0. If left height and right height both completely balanced, then the balance factor is 0. If the left height is less, right height is more, so in that case you will get -1. If the left is more but right is less, so it will be +1. If in this 3 values comes, then it is completely balanced. If it is not in this 3, then it is imbalanced. So it requires rotation. And remember, there are two important type of rotation. One is single rotation, second is double rotation. Single rotation, again, two categories, either left rotation or right rotation. The left rotation is called LL rotation and the right rotation is called RR rotation. Similarly, double rotation comes either in the left-right rotation or right-left rotation. The right-left rotation is called LR rotation and right-left is called RL rotation. So these are the 4 varieties of rotations you can do for balancing the binary search tree. Once it is rotated properly, then the balance factor will be either between, means in the range of 0 or -1 or +1. So remember, where you have to do these rotations, because sometimes the data may come completely right side or the data may come completely left side. Whenever that type of scenario comes, you have to rotate it so that the balancing will be done properly. If you observe here in this tree, A, B, C, assume there are 3 nodes and the values are like this, 2, 1, 0. Now, if you observe here, the complete data comes right side. It is dominating towards right side. It is right balanced tree. It is unbalanced, completely right side. Right side is unbalanced. When the data is completely right side, then you have to rotate towards left. If rotate towards left, then this is called LL rotation. Now please observe here, A, B, C completely comes towards right. So you need rotate left side. If you rotate left side, then that rotation is called LL rotation. What rotation? LL rotation, because you have to rotate towards left. So now B become parent. So B is now parent node and A become left side, because this is you are rotating towards left. It will left and the C become right. So A left, B right. Then it is a balance. So this type of rotation is called what? LL rotation. So LL rotation will be done whenever the data goes completely towards right. So this is right side. Whenever the data goes right, then go for left rotation. Similarly, if you think about the real data in binary search tree, please observe here 1, then 2, because 2 is greater than 1 comes right side, then 3 is greater than 2. So this data is completely goes towards right side. Now this scenario comes under which rotation? This comes under LL rotation, because the data is completely goes towards right side. So if you rotate it now, 1 become left side of 2 and 3 become right of 2. So now this is completely balanced. So 2 is now my parent node or root node and 1 is my left and 3 is my right. Now the balance factor for 2 is 0. The balance factor for 1 is 0. balance factor 3 is, now it is completely balanced. So it is a AVL tree. If you think about this tree, now think about the CBA. Now it is completely dominating towards left side. So it requires rotate towards right. If you rotate towards right, then this become balanced tree. So this type of rotation is called what? RR rotation. Now if you think about the 3, 2, 1, it is a binary search tree. But what happens? All the data comes towards left. Now if you rotate towards right, then the 2 become parent and 1 is left and 3 is right. So now it is a complete balanced tree. So whenever data completely comes towards left side, then rotate right side. Then this rotation is called what? RR rotation. So this LL and RR comes under single rotation because you are rotating only once. Now think about, there is another rotation called LR rotation. That means when the data comes towards left side as well as and then right side. For example, I am having the data like 3, 1, 2. 3 is my initial data. Then 1 comes, 1 means left of 3. Then 2 comes, 2 is greater than 1. If 2 is greater than 1, insert towards right. But it is a binary search tree, no doubt. Binary search tree, but it is imbalance. So my imbalance tree, I have to balance it. How to balance it? Because this type of tree requires double rotation. That means 2 time rotation. First, you have to arrange the data in a proper way first. Now, if you think about the 3, 1, 2, this is comes under what? LR. LR case. That means left and right side. Then you have to rotate 2 times. First, what I will do? These 2, I will rotate towards right. So, right rotation I need. So, after rotating, I will get 2 and 1. So, 1 become child of 2. So, this become 3, 2, 1. Once 3, 2, 1 comes, it completely towards left side. So, now I have to rotate right side. So, I need RR rotation. After right rotation, that 2 become my parent and 1 and 3 become left and right. So, this type of rotation is called what? LR rotation. So, LR rotation requires 2 times rotation. That is called double rotation. LR comes under double rotation. Now, you can see the diagram. 2 is parent, 1 is left child and 3 is right child. It is completely balanced. Similarly, there is another rotation called RL rotation. RL rotation. The RL rotation requires whenever the data goes towards right side and then left side. Now, if you think about 1's right is 3, 3's left is 2. Now, what happens? RL. Whenever this type of binary search tree comes, you have to rotate properly. Now, if you observe here up to here it is balanced. But if you think about the 2 means 1, it is imbalance. It is imbalance. So this comes under what? RL case. So it requires 2 time rotation. What I have to do? 2 time rotation. First, rotate this towards right side. If you rotate right side, now this become 2 is become middle node and 3 is rightmost node. Now this is complete towards right. So when the data goes towards right, again rotate left side. So the 2 become parent, 1 left. So this type of scenario is called what? RL rotation. So here now see the balance factor. Balance factor for 2 is 0, for 1 is 0, for 3 also 0. So it is completely balanced. So you have seen the 4 types of rotations. Now you can see the procedure for the insertion operation. The insertion operation is performed. Insert a new element into the binary tree using binary search tree property. After insertion, check the balance factor of every node because every node plays major role. If at all it is imbalanced, then you have to rotate. So if the balance factor of every node is either 0 or 1 or -1, then go for next operation. That means next insertion. Otherwise, if it is not in this range, then the tree is imbalanced, you have to rotate it. So after rotation, then the tree become balanced. Once tree is balanced, then you have to stop it, the operation. Okay, let us have a small example. Now I want to insert the data from 1 to 8 in a binary search tree. So while inserting the data from 1 to 8, then I have to check the balancing factor. Check. First one is root node. So up to this no problem. Its balance factor is 0. So it is balanced up to this one. Now insert 2. If you are inserting 2, because 2 is greater than 1, comes right side. So it is balanced. Now for 1, balance factor is -1. Why? Because left height is 0, right height is 1. So 0 minus 1 is -1. Because always you have to subtract left height minus right height. So here left height is 0, right height is 1. So 0 minus 1 is -1. 0 minus 1. For 2, left height is 0, right height is also 0. So 0 minus 0 is 0. So up to this no problem. Now when you insert 3, now what happens? 3 is greater than 1, come right side. 3 is greater than 2, come right side. So the data is completely one side. So it is imbalance. So which side is now? Right side. So whenever the data comes towards right, then rotate towards left. So it requires left rotation, LL rotation. So while left rotation, this become parent, and this is A, this is B, and this is C. So B become parent node, and A become left child, and C become right child. So this will be the final tree, and this tree is your balance tree. So that means you have inserted up to 3. I told you have to insert up to 8. Now next is 4. Now you have to insert 4 where? Because this is the final tree. So in this tree you have to insert 4. So when you are inserting 4, what will happen? 2's right and then 3's right. So the 4 will be inserted after 3. Yeah. Now think about you are inserting 4. So when you are inserting 4, the 4 comes towards right of 3. So now if you observe here, 2's height balance factor is -1 because left height is 1, right height is 2. So 1 minus 2 is -1. So -1 is allowed. Similarly, if you think about the 3, this side is 0, this side is 1. So this side is 0, this side is 1. 0 minus 1. So -1. For 4, no. So it is up to insertion 4, it is balanced. There is no problem. Now insert 5. When inserting 5, 5 comes right after 4. So it is imbalance. Now for node 3, the balance factor is -2. So whenever the balance factor is -2, it is not allowed. It is imbalance. So you have to rotate. Because now the data comes towards right. So rotate towards left. It requires left rotation. So if you rotate this, the 4 become parent node, and 3 become left, and 5 become. So this is the final AVL tree up to 5. Because our goal is insert up to 8. The next node is 6. Now where you have to insert 6? Because 6 means which is greater than 2, greater than 4, greater than 5. That means it will come after 5. Come after 5. Now you are inserting 6. Now when you are inserting 6, it comes right of 5. Now because I told you after every insertion you would calculate the balance factor. Now for 6 balance factor is 0, for 5 1, for 4 -1, whereas for 2 it is -2. It is imbalance at this place. So that means these 3 nodes are imbalance. So you have to balance. So it requires LL rotation because the data comes towards left, means right. When the data comes towards right, you have to rotate towards left. So that is imbalance. So that it become balanced one. So now after balancing, this 4 become my parent, and 4's already right data are 5 and 6, so they will be right as it is, and 4's left to become 2, and already the original 4's left means the left child is 3, that become my 2's right, and 2's left is already 1, so 1 will be as it is. So it is now balance. So the tree is balanced one. Okay. So up to this you have inserted up to 6. Now you have to insert 7. If you want to insert 7, where you have to insert? Because you have to insert right of 4, right of 5, right of 6. So if you insert 7, at 5 it is imbalancing. Please observe here. because balance factor of 5 is minus 2. Minus 2 is not allowed. So again rotate it. So this is again data is completely towards right. Again rotate left side. So when you are rotating left side, now 6 become root and 5 is left and 7 is right. So it is now balance. Now you have to insert 8. After inserting 8, now insert after 7. So there is no problem at all. So the tree is completely balanced. So this is the final AVL tree after inserting the data from 1 to 8. Now let us see one more example to insert the value like this 63, 9, 19, 27, 18, 108, 99, 81. So now you have to insert this following data. First 63 comes. So 63 is the parent. Then 9 comes. 9 is less than 63. So left of this. So up to this it is balanced. Next 19 comes. When 19 comes, 19 is less than 63 and 19 is greater than 9. So right of this. So when you think about this tree, it is completely imbalanced. Height imbalanced tree. So it requires lower test. Left or LR rotation. So when LR rotation comes, because this is A, this is B, this is C. In LR rotation, always C will be the parent. In LR rotation, C will be always the parent. So 19 is parent. And B become left of C. So this. And A become right of C. So this. So this is C. This is B. And this is A. So C, B, A will come. So you should know whenever LR rotation comes, you make C as a root and your B as left of root and A is right of root. So up to this, it is in a balance. Now if you think about the balance factor of every node, it is 0, 0, 0. So it is completely balanced. Now next data is 27. Now 27 is greater than 19 and less than 63. So come this. So when you think about this, this is also completely balanced. So no need to go for any rotation. Next data is 18. When the 18 comes, nine is right. Because 18 is greater than 9, come this side. So 63 and 27 as it is. So this is also completely balanced. So up to this, there is no problem at all. Now 108 comes. 108 means greater than 19, greater than 63. So it is also completely balanced. So there is no disturbance in the balance factor. So when there is no disturbance in the balance factor, no need to do any rotation. Now next is 99 comes. When the 99 comes, you have to insert after 108. So if you think about now this tree also, everywhere the balance factor is within the range. So there is no problem. Now when the data 81 comes, you are inserting 81. After inserting 81, now data completely imbalanced here. Please observe here 108, 99, 81. So it is completely dominating towards left. That means the data comes towards left. So it requires right rotation. Now in the right rotation, if think A, B, C, B will be the parent. So B will be the parent node. And A will be the right and C. So this is now balanced. So after this, now if you observe here, the balance factor is between 0 or 1 and 1. So it is now purely balanced. Okay. Now we'll see the deletion operation. So in AVL tree, you can do either insertion or deletion also. So while deleting also, you have to delete based on the binarity property. At the same time, you have to maintain the balance factor also. So the deletion operation in AVL tree is similar to deletion operation in binary search tree. Because while deleting the node, you have to check the balance factor of left tree as well as right tree. If at all anything is imbalanced, again you have to balance properly by rotation. Now you think about this tree, A, B and B having 2 subtrees and A having 1 subtree. Now if you want to delete the node X, that time if the balance factor is 0, that means you are talking about the B's balance factor. If the balance factor is 0, then B become parent Please remember, whenever the balance factor is 0 for B, then B become parent and B is left, the T1 is left of this, and this node you want to delete, this node X. Then A is always right of the B and the T2 will be left of A, and T3 will be right of A. Okay, let us see a small example here. Now we are talking about what? R0 rotation. R0 means when the balance factor of B is 0. Balance factor of B is 0. Let us see a small example here. Assume there is a tree. The tree with following values: 20, 20's right is 30, and 20's left is 10, because binary search tree property. And 10's right is 15, and 10's left is 5. So now this is a AVL tree as well as binary search tree. Now here in this tree, you want to delete 30. So whenever you are deleting 30, you have to find its corresponding B. Who is the corresponding B? This is always A, this is always B. Remember. Now B's balance factor is how much? 0. So it requires R0 rotation. R0 rotation. In R0 rotation, what will happen? The B become parent. B become parent. If B is parent, A will be right of this. A will be right of this. Now observe here. Now you want to delete 30. If you want to delete 30, now the corresponding sibling is B and your parent, that is A. So there what you have to do? Because now this A is your critical node, that you have to balance properly. Its height must be balanced. While deleting, you make, I told you, this B will be parent node after deletion. And the critical node A become its right, and B, the B's left child, the 5 will be as it is left only, and 10's right, how much? 15. The 15 will go towards right of this, but already you made this A is the critical node is the right of this, so you make the values left of this. So this is the property of R0 rotation. R0. So whenever the B having balance factor 0, then you have to follow this property. What is that? The B you make as a root, and the critical node you make that as a right of this, and already B's left is there as it is, no need to change, that is left of this. But B's right data, that you have to adjust. Where you have to adjust? You make the critical nodes left side. Critical nodes left side. So this rotation you have to follow. This is R0 rotation. Means 0 stands for what? Balance factor of B. Balance factor of B. Because balance factor of B is 0. Next. Think about R1 rotation. That means the balance factor of B is 1. If A is root and B is 1 child node, T3 is 1 tree, and T1 and T2 are 2 subtree. In this tree, if you want to delete one node X, then the B become parent and A become right child of B. The T1's height will be left as it is, and T2's will be left of T2, and the T3 already available in A, that is right of A. So this is the way you have to delete. Let us see through a small example. Assume there is a tree with root node 30, 40 and 60, 30, 45, 55, 10. Assume you want to delete 55. If you want to delete 55, now you have to delete 55. So if you want to delete 55, how will you do? Let us see. Now 55, the parent is A, means 60. Now their corresponding sibling, that is 40, whose balance factor is 1. So it requires R1 rotation. So whenever you want to delete this 55, you make the critical node, that is 50 as parent node, means sorry, this is the critical node, and the corresponding is B, node B. Always make B as a root node always. And A, you make as right of this, right of B. And 40 is left already, 30 and 10, you keep as it is, no need to change, because left will be always left only, because it has to follow the property of binary search tree. After that, 50 is right, already 60 is there, so that will be right of this. Only the thing is, the B's data, which is 45, now this has to be kept properly, because it has to follow the property of binary search tree. Now you keep this of this, so it is now completely balanced. So while deleting this type of data, you must be careful. It has to follow the property of binary search tree, at the same time balancing factor. Now please observe this tree now. Okay, so while deleting this data, you have to find which is A and which is B. Always you find your parents siblings, that is B, and your parents grandparents, that is A. So your sibling, the B will be always the root. Then root left will be left, and the B, the critical node A, become right of this, right of this. Now 50's right is always 60 as it is, and B's right data you have to balance properly. So make 50's left, so that it is balanced. So it will be maintaining the balancing factor also. Okay. Similarly, there is something called R with -1 rotation. That means the -1 is what? Height of, means the balance factor of B. So in the previous session you have seen R0, R1, R-1 now. R-1 rotation is performed if B, node B has balance factor -1. Balance factor -1. This case is treated in the same way as LR rotation. In this case, the node C, which is right child of node B, become the root node of the tree B, and A is the left child. A is its left and right children respectively. Okay. Now, if you think about this, now if you want to delete this node X, then you have to find which is B and which is A and which is C here. So this is your -1 case. Whenever B is having -1 case, then you make C as a right parent node, C as a parent node, and make B as a left child and A as right child. This case you should remember whenever you are going for R1 with -1 rotation. That means if the balance factor of B is -1, then the C become parent and B become left and A become right. So this is the way you have balance. Now let us take a small example here. Now if you want to delete 60, its corresponding B, because it is having no child, no. So this is comes under R with -1 rotation. Balance factor of B, this is B, this is C, and this is A. So whenever R with -1 case comes, what you have to do? Make C as always root. C as always root. Nothing. Whenever you want to delete 60, you make, because this is A, this is B, this is C. You make C as a root. C as root. After making C as a root, make B as a left and make your A as right. So the formula is C will be always root node and B will be left child and A will be right child. So if this tree comes in this form, this will be always completely balanced. At the same time, it is a binary search tree also. So this is the way the deletion happens. Okay. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.